This is the reason why you'd find that sometimes the delta x, the displacement in the x, will be written as the displacement in the y. Equation 6 into equation 4, what we called equation 4. This is the reason why when you go to your questions in textbooks or question papers, they will always say on the statement that the object moves at a constant acceleration. So far, we have derived 3 equations of motion. I hope you find this to be a fun activity, and it builds confidence in terms of you using the information sheet that is provided when you write your tests and exams. Out of all the 3 equations that we've derived so far, they all have time as a variable in them. So if we go to the first equation of motion, you can see that there is time there as a variable. There is also time on the second equation of motion as a variable. We also see that the displacement is dependent on the time as well. Now, this calls for a need of deriving an equation that does not depend on time, that does not have time, right? In order for us to do this, we are going to take equation 1, the first equation of motion, this equation here, and combine it with equation 4, which we said is the second equation of motion, so that we eliminate the time. So I'll make the time the subject of the formula and then substitute in equation 4 from equation 1 to then eliminate that. How do I mean? So I'm going to then argue to say using equation 1, which was defined by final velocity is equals to initial velocity plus the acceleration times change in time. Now here I'm going to make time subject of the formula because I want to eliminate time. So this means here that I'll have final velocity minus initial velocity. I'm taking this to the side. It will be negative when I transpose that. So that I'm left here with a times change in time. Now if I divide both sides by the a and the a here, it will cancel. Wait, it will only cancel from one side, so that I'm only left with change in t is equals to that. So this means here that our change in t will be defined by the final velocity minus the initial velocity over the acceleration. I'll call this equation 6, following our numbering of equations as we deriving them. Now I'm going to substitute. Now where is equation 4? Equation 4 is this beautiful equation here. I'm going to put the time here right from the equation 6. So this means now that we will have the change in x is equals to vi plus vf divided by 2. Remember that here we used to have change in t, and I'm saying now the change in t is given by that. So this means here I'm going to have vf minus vi all over the a, right, which is this guy here. Now from here, deriving this equation becomes very, 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 very boring because it's just mathematics and solving this equation. Now to solve this, we will then say change in x, the displacement. Now here I'm going to rearrange this here. I'll start by writing the v final, this one here. Remember it is still positive, and I'll add that to the v initial. Alright, remember it is still positive, right? And I'm going to put brackets here, and I'm going to keep this as it is, but I'm going to write this as in brackets. Now, the 2 and the acceleration, I'm going to multiply these two so that I have a big division line like that that says 8 times 2, right? The twice the acceleration times 2, right? Notice that here at the top, the reason why I was rearranging this is that I can see that this is a difference of 2 squares. I hope you are able to see that. This here is a difference of 2 squares, right? Just to remind you, I'm saying here that if you were to have x plus y and you were to have x minus y, this would be x squared minus y squared. And we are going to do exactly that in solving this problem. So this here I'm going to have final velocity squared minus initial velocity squared. This guy here will give me this here, right? Because the difference of 2 squares. So this will be divided by 2a. So that now I'm going to cross multiply by this, and then I'm going to have 2 times a times delta x is equals to v squared minus vf squared minus vi squared. I'm going to take the negative vi squared to this side, right? So that it will be positive when it comes to this side, and I'm going to be only left with final velocity. So this will give me final velocity squared is equals to initial velocity squared plus 2a change in x. And this is the fourth and our last equation of motion. And again, it is only used when the acceleration is constant, because it was a combination when we derived this equation of the equations that we derived from the fact that the acceleration is constant. So this means also this equation can only be used when the acceleration is constant. And as far as solving our problems, this will be equation 7, because we're numbering them from 1 to 7 as we're solving this, deriving these equations, right? Now, this formula is used when time of motion is unknown, right? Because we deliberately eliminated time, right? That's why in this equation we don't have time. So if we don't know the time, we can use this equation to find any of these variables, depending on whether they've given you 3 of these variables to solve these equations. Now, in a nutshell, we then have our 4 equations of motion defined on our formula sheet as the final velocity is equals to the initial velocity times the product of the acceleration and time. The other one says the final velocity squared is equals to the square of the initial velocity plus twice the product of the acceleration and the displacement. The other one says the displacement is equals to the average velocity, right? Because we're adding the 2 and dividing by 2 times the time. So it's the product of the average velocity and time. And the last equation says delta x is equals to the product of the initial velocity plus half the acceleration times the square of the time. All these equations are true when the acceleration is constant. It means they're giving you a hint, or they're saying that you can solve that problem using any of these equations, right? I hope this was fun and you're getting answers to why you are always using these equations on your formula sheet. These 4 equations that we have just derived can also be used in the vertical direction, meaning that if we were to have the reference frame that is sitting like this, here this is our y and this is our x, and we have an object that perhaps is going up like that or going down like that, as in vertical projectile motion, right? We can still use these equations. We can still derive the same equations. We can have the same equations because we know that in this motion, if it's a free fall, right, meaning there are no any other forces, our acceleration would be equal to the acceleration due to gravity, which is a constant number, 9.8 meters per second squared. Because the acceleration is constant, we are able to derive the same equations. Even in this one here, we still have the same thing, or we can write this as change in y. So we can use the same equations. So that's the reason why in your formula sheet or your information sheet, you'll find that we write them both in x and y, because the conditions for these equations to exist are still true. Which other formula do you find fascinating on the information sheet and you always have wondered where it comes from? Drop that formula in the comment section and I'll do a video deriving that equation for you.